So this presentation is basically about understanding the phenotypic variations that can be observed in banana plant or Musa sp. So here in the first slide, I have generated a principal component analysis on the different variables in my data. These are the outer curve, the inner curve, the pedicel length, the pedicel circumference, banana circumference, and the number of sides. On the left side here, I have the first three principal components and its cumulative variation of 87%. This means that 87% variation can be explained using principal component 3. On the right, we have the loadings from the three principal components. In this study, I will be interpreting PC1, and basically it indicates that the longer the bananas are, the higher positive PC1 scores they have, while the shorter banana length, they have lower PC1 scores. We can also see that the skinnier the banana is, the lower positive PC score it has, and the wider the banana circumference, the higher positive PC scores that it has. So here in this slide, we have a box plot and the different statistical tests that was used to describe this box plot. So the box plot basically represents the relationship of principal component 1 scores between the location of banana purchase. So either the bananas were bought in Kitchener-Waterloo or outside of Kitchener-Waterloo. The box plot represents, or the box in the box plot represents the middle 50% of data that was collected, and the middle horizontal line represents the median. The box itself represents the interquartile range, and the whiskers extend to the minimum and maximum values that are not outliers. The outliers are defined as any values that falls 1.5 times outside the interquartile range and is denoted by a circle. So now I'm going to discuss the different tests that I used to describe this box plot. Firstly, we did a Shapiro-Wilks test to test for the normality of the two variables. And looking at the p-values that we have here, they're both normal because they're both greater than 0.05. And since they're both normal, I use the f-test to check for variances. And again, the p-value is greater than 0.05, so that means that the variances between the variables is homogeneous. And since the variances are similar between groups or variables, we're going to be using this Welch's two-sample t-test to compare the means between the groups. And again, we have a p-value greater than 0.05, which indicates that we have the same means between the group. I also calculated the effect size for this data, and then it was negative 0.2175 with a 95% confidence interval of this value right here. I also did a power test for my two-sample power test, and it was 0.1889, or 19% of the time the null hypothesis can be rejected, which is fairly small. And to be able to reject the null hypothesis 80% of the time, we need 332.5 sampling in each group, or 333 samples in each group. Going back to the Welch's two-sample t-test, since we have a p-value greater than 0.05, it denotes that there's no significant difference between the principal component 1 scores between KW and not. So again, in this slide, we have a box plot that describes the relationship in banana circumference between different company of import of the bananas. So Chiquita, Del Monte, and Dole. When able to describe the difference or the similarity of means between the variables, we needed to do like some statistical tests. First, we needed to do the Shapiro-Wilks test to test for normality of the groups, and from these values that we have here, they're all greater than 0.05, so they're all normal. And now we can move on to the Bartlett's test, since all of our variables are normal. And we have a value of 0.2193, again greater than 0.05, denoting similar variances among the groups or the variables. And so we're going to move on to the one-way ANOVA test to describe the differences or similarities of means between the group. And again, we have a p-value that is greater than 0.05 that basically denotes that the means between this company of imports are all the same, and therefore this letter here is all the same. So according to this table here, using the random effects ANOVA, we have a within group variance of 0.995 and a between group variance of 0.0053. That's fairly small, and actually that's going to be negative. So basically what it's saying is that there's no between group variances that is observed in the three different species, and that 99.5% could be attributed within group variation. Therefore, 0.5% variation in banana circumference is due to the import company of bananas, and another 99.5% is due to the variation within the banana circumferences. So here in the slide we have a scatter plot that basically describes the correlation between the length and the width of the banana by using the inner curve length and the banana diameter. So here we have a correlation coefficient of 0.058, or what statistically means is that 5.8 of all variations observed in the inner curve length of the banana can be explained through the variation that is observed in the banana diameter. However, though, this doesn't mean that they have a causative relationship, because this only explains the variation in the banana inner curve length through looking at the banana diameter. As seen on the scatter plot, there is a positive correlation between the length and the width of the bananas. The Shapiro-Wilks test indicated that both variables were normally distributed, since they have a p-value greater than 0.05. And by using the studentized Bruce-Pagan test, we were able to find out that the variances between the groups were the same, because the p-value is again greater than 0.05. It's 0.927. This then led me to use the Pearson's product moment correlation to compare the means of my variables. So the p-value was 0.164, which is again greater than 0.05, and therefore there's homogeneity of means between the inner curve length of the banana and its banana diameter. Also, going back to the scatter plot, the diagonal red line that we observe in the graph represents the correlation of the banana's inner curve length and the banana's diameter. The slope was 1.372, which was significantly different than 0, as the p-value is 0.01, which is less than 0.05. Similarly, the intercept of 11.726 and have a p-value of 1.17 raised to the -7, which basically means that it's definitely significantly different than 0. And again, the regression line in the graph represents a positive correlation between bananas' length and bananas' width. So here in the slide we have the two-way ANOVA test results done on the relationship or the effect of the light treatment or storage treatment on the ripeness index of the banana. Here in the top table we can see a two-way ANOVA test results, and it showed that there was no significant interaction of light treatment and storage treatment to the ripeness index of the banana, which basically means that there's no effect of light treatment or storage treatment on the ripeness index. This is true because the p-value of the two-way ANOVA tests are all greater than 0.05. So in the second table, we have a comparison or analysis of variance table comparing the two models, the simple one and the complicated one. And from the result that we have here on the p-value, that means that using the complicated model didn't make describing the variation any worse, because it's greater than, the p-value is greater than 0.05. So then we use this model, model 2, here to compare it to another model if we take out the light treatment. So here we only have comparing storage treatment, the effect of storage treatment to the rightness index. And with this comparison, we have a p-value of 0.2806, which again is greater than 0.05. And it basically means that this model right here didn't make the describing the variation any worse. And so all the models were all adequate in describing the significant interaction of LT and ST on the ripeness index of bananas. And the interaction could be seen on the next slide. So in relation to the previous slide, these are the box plot that was generated for comparing the ripeness index on the storage treatment and the light treatment. So here we can see they're fairly the same, on like the same kind of range here. So we might think that there's no significant difference between the dark and light in compared to their means. But regarding the p-values and all that, the light in the light treatment, the light variable had a p-value of 0.16 and the dark variable had a p-value of 0.29. And for the storage treatment, the apart variable had a p-value of 0.16, while the together had a p-value of 0.93. So since all of them are all greater than, or like the p-value are all greater than 0.05, that means all of the variables are normally distributed. So then we're going to check their variance, and the results were that in the light treatment we had a variance or a p-value of 0.32, again greater than 0.05. That means similar variances between these groups. And in the storage treatment we had a p-value of 0.61, and again p-value greater than 0.05 denotes homogeneous variances between the two groups. Lastly, we did a t-test to compare the means of the groups to confirm that they actually have similar means. And from the t-test, we had a p-value for the light treatment of 0.12, and for the storage treatment of it's 0.73. So again, we know that the means between the two groups of each treatment have similar means because their p-values are greater than 0.05. So in relation to the last slide, since there are similar means between the variables in each treatment, that means that there's no effect of the storage or light treatment on the ripeness index of the banana. And that ends my presentation. I would like to thank Hugo, Flavio, and Dr. Tristan Long for helping me get through coding everything and doing troubleshooting for this major assignment. It was deeply appreciated because I wouldn't have done it without you guys. I also would like to thank my homework buddies, Kobe and Lucy. They've been there with me this whole time. They were there to motivate me to finish this major assignment. They're amazing. And I would also like to thank my BI 393 classmates because we all did it together. We went through it together and they're all amazing. So, thank you.